to the infinite cyclic group Z, but the other homology groups are 0. So Poincaré made a conjecture. He said if X is a 3-manifold and the homology groups of X are isomorphic to the homology groups of S3 for all K, does it follow that X is homeomorphic to S3? This is Poincaré's first conjecture. And Poincaré's first conjecture is not so well known because it's false. So it turns out the answer is no. If you take a solid dodecahedron, so this is a regular polyhedron where each face is a regular pentagon, and you glue each face to the opposite face by rotating it 36 degrees, this gives you a 3-manifold Y that has the same homology groups as S3. So you can't use homology to figure out if the space Y and the space S3 are homeomorphic. You need something else. In 1904, Poincaré introduced a new invariant, the fundamental group. If the 3-manifold Y is not homeomorphic then these are not homeomorphic because the order of the fundamental group of S3 is 1, and the order of the fundamental group of Y is 120. So after Poincaré realized this, he revised his conjecture and asked the conjecture, if X is a closed 3-manifold and the order of the fundamental group of X is 1, does it follow that X is homeomorphic to S3? And this is the Poincaré conjecture that most of you folks are familiar with. And the answer is yes, as was proven by Perelman in the course of 3 archive preprints that were posted between November of 2002 and July of 2003. As a side note about this interesting space Y that Poincaré introduced, in 2003, the French astronomer Jean-Pierre Luminet raised the possibility that the shape of the universe that we live in is Poincaré's space Y. That would be kind of odd because Y is a compact 3-manifold, and we don't necessarily think of the universe as being closed and bounded, but it's possible. Okay, so this is sort of a motivating example coming from topology. Most of the rest of my talk will be about talking about situations where you have invariants in number theory and where those invariants don't allow you to classify the objects that you would want to classify. So here's the first example, positive definite quadratic forms. So a quadratic form is a homogeneous polynomial of degree 2 in some number of variables R. We say that the form is positive definite if Q of X is greater than or equal to 0 for all possible inputs X. It doesn't matter if you take the inputs from Z or the inputs from R. These are the same. And if Q of X is equal to 0, if and only if the inputted values for X were all 0. We say that two forms are equivalent if there is an invertible integer linear change of variables that will take you from Q1 to Q2. So this is a natural notion of equivalence. The quadratic forms x squared plus y squared and x squared plus 2xy plus 2y squared are equivalent because you can get from x squared plus y squared to the other form by replacing x with x plus y. That linear change of variables is given by an integer matrix. It also has an integer inverse. So those forms are equivalent. So associated to a quadratic form Q, we can make a generating function, theta sub Q of Z, where for every single non-negative integer n, we count the number of vectors x in Z to the R, that when you plug them into the form Q, you get the number n out. So this theta sub Q of Z is called the theta series of Q, and it's a modular form, which lots of people at the University of South Carolina know about. It's a modular form of weight R over 2. That means that it has transformation laws that relate the value of theta sub Q to values at other. Sorry, if you pick a number Z, then there's a relationship between the values of theta sub Q of Z and values of theta sub Q when you apply linear fractional transformations to Z. And this comes from a general version of the Poisson summation formula. Okay. So the question is this: if we have two quadratic forms Q1 and Q2 that have the same theta function, does it follow that the quadratic forms Q1 and Q2 must be equivalent, that there's some invertible linear change of variables that will take you from Q1 to Q2 and vice versa? So this is connected with the question, can you hear the shape of a drum? This question was popularized by this article that Mark Katz wrote in the 1966 Monthly. In particular, if you have a quadratic form Q in R variables, you can associate to that form Q a flat torus in R to the R, where the spectrum of the Laplacian on that torus is determined by this theta sub Q. So if you have two quadratic forms Q1 and Q2 with the same theta function that are not equivalent, those give you examples of isospectral flat tori. Isospectral meaning they have the same spectrum, which means they would have the same sound if you would vibrate them, that are not isometric. Okay? So here's the answer to the question, does it follow that the quadratic forms have to be equivalent? The answer is no. So here's an example that Sheeman found in 1990. Here are two quadratic forms in 4 variables. They both have discriminant 1729. They're not equivalent, but their theta series are equal. So for every single positive integer n, the number of ways you can write n in the form Q1 is the same as the number of ways you can write n in the form Q2. On the other hand, if Q1 and Q2 are positive definite quadratic forms in 3 variables, and their theta series are equal, then the quadratic forms must be equivalent. So the answer is, for quadratic forms in 3 variables, yes, if their theta series are the same, the forms must be the same. But in 4 variables, no. And similarly, the answer will be no in higher dimensions too. So at the end of my talk, I'd like to give just some sort of general philosophical thoughts about reasons that this invariant, the theta series, is not enough to classify a quadratic form up to equivalence. There's some more examples of these that were found. So Conway and Sloan discovered a 4-parameter of families of pairs of quadratic forms in 4 variables. They showed that if you take a form Q1 and a form Q2 from these respective families, L plus and L minus, that depend on these parameters A, B, C, and D, then the theta series of Q1 and the theta series of Q2 are the same. Of course, the theta series doesn't tell you if Q1 and Q2 are equivalent. Conway and Sloan thought that the forms Q1 and Q2 are not equivalent, but they couldn't prove it. They conjectured that, and it was proven in 2012 by Servino and Hein, by introducing new invariants to show that these forms were actually not equivalent. Any questions about this example? All right. So the second example is the objects are number fields. What is a number field? A number field is a finite degree field extension K over Q. Contained in K is sort of a natural ring to work with that's somehow analogous to the set of integers. It's called the ring of algebraic integers. These are the elements of K that are roots of a monic polynomial with integer coefficients. Every non-zero ideal in this ring OK is a subgroup of finite index, and we define the norm of an ideal to be the order of the quotient ring. The reason that we work with ideals instead of elements of OK is that every ideal of OK factors uniquely as a product of powers of prime ideals. This is an analog of the fact that every integer can be written uniquely as a product of powers of prime numbers. We say that a prime P ramifies in the field K if when you factor the principal ideal generated by P in OK, it factors in this way where at least one of the exponents is greater than 1. So the primes that ramify in K are the primes for which this ideal, the principal ideal generated by P, is not square free. Here's the invariant. The Dedekind zeta function of a number field k is this object. It's a function of a complex parameter s, and it's the sum of the reciprocals of the norms of all of the non-zero ideals in OK. So if K1 and K2 are isomorphic number fields, that isomorphism will send the ring of integers in K1 to the ring of integers in K2, and will give you an isomorphism of those rings. And that means that the Dedekind zeta functions will be equal for every single complex number S. The question then is it true that if I have two number fields with the same Dedekind zeta function, that the number fields themselves must be isomorphic? The theme of this talk is the failure of injectivity, so it's not hard to guess that the answer is going to be no. We say that two number fields K1 and K2 are arithmetically equivalent if their Dedekind zeta functions are equal for all S. That means they have the same number of ideals of norm K for every single positive integer K. If K1 and K2 are arithmetically equivalent, then the extensions must have the same degree. They must also have the same discriminant, and they must also have the same normal closure. In 1977, Perlis showed that if K1 and K2 are arithmetically equivalent and have degree less than or equal to 6, then they must be isomorphic. However, he also gave an example of a pair of degree 7 fields, x to the 7th minus 7x plus 3, and this number field defined by this degree 7 polynomial, that are arithmetically equivalent, but that are not isomorphic. Some folks might have seen this x to the 7th minus 7x plus 3 polynomial before. It's a degree 7 polynomial whose Galois group is GL3 of F2, the unique finite simple group of order 168. So moving on to a third example, I'm going to talk some about trinomials. So for me, a trinomial is a polynomial of the form f of x equals x to the n plus ax plus b. We say that two trinomials f of x and g of x are equivalent if you can make a change of variables of this sort to turn g into f. The assumption that c is non-zero means that if f is equivalent to g, then g is also equivalent to f. If f and g are equivalent and they're both irreducible, then the quotient q of x mod the ideal generated by f of x and q of x mod the ideal generated by g of x are isomorphic number fields. There's a way of choosing sort of a canonical representative out of an equivalence class of trinomials. If I have a trinomial of the form x to the n plus ax plus b, and a and b are both non-zero, then there's some number t, some rational number t, so that f of x is equivalent to this, x to the n plus t, x plus t. So we have a map from non-zero rational numbers with the property that x to the n plus tx plus t is irreducible to degree n number fields, where the map takes a polynomial to the number field q of x mod the principal ideal generated by x to the n plus tx plus t. And of course, the question, as always, is this map injective? Do different values of t give me different number fields? So for fairly simple reasons, this map will fail to be injective when n is equal to 3 or 4. It's not hard to take any cubic polynomial and make a linear change of variables to make the coefficient of x squared become 0. And because you can do that for any element, any of the infinitely many elements in a degree 3 number field, you can get many different trinomials that define any cubic number field. It's a little bit harder in the degree 4 case, but it is possible to come up with number fields that have infinitely many trinomials that define them. There's a paper from 2000 in which Spearman and Williams determined all of the quintic fields, degree 5 fields, that can be defined by a trinomial x to the 5th plus ax plus b with a equals 0, and also with another trinomial where a is not 0. I'll mention their family later. So I worked on this question with a master's student, Jesse Podsolek, and in 2017, we wrote a paper where we talked about fixing a quintic number field, and then trying to understand all of the trinomials that have a root in that quintic number field. So associated to that number field k, there is a curve c sub k defined over q, whose rational points are in bijection with the non-zero numbers t in q, with the property that k is defined by x to the fifth plus tx plus t. This curve has genus 4. I'll say a little bit more about what that means. The genus of a curve is can be thought of in the following way. If you take a curve and you look at the complex points on that curve, you can give that object the structure of a Riemann surface. And that Riemann surface has to be either the Riemann sphere with no holes, a donut with one hole, a donut with two holes, etc. And the genus is simply the number of holes in that Riemann surface. So if you have a curve C over Q that is smooth and has genus 0, then the rational points on C are non-empty if and only if C has points over every completion of Q. So you can determine whether your curve has points in each completion, and then from that figure out whether it has rational points. So in the situation where it does have a point over every completion, it has to have infinitely rational points. If you have a smooth curve of genus 1 and the set C of Q is non-empty, you can your curve is isomorphic to a curve of the form y squared equals x cubed plus ax plus b, namely an elliptic curve. If you have a curve of genus greater than or equal to 2, there isn't necessarily a nice way to figure out if it has points on it or not, but it's the theorem of Falting's that the curve only has finitely many points. And in number theory, a lot of people sort of have this belief that a curve of genus greater than or equal to 2 should have no points at all unless there's a good reason it should have points. So keep this in mind, both in this example and with the later examples. So there's some number field k for which this curve C sub k has no rational points at all. For example, you can't have a totally real degree 5 number field be defined by a trinomial just because a trinomial can't have 5 real roots. So there are also p-adic restrictions for other primes p. If you look at this polynomial f of x equals x to the fifth minus 5x plus 12, whose Galois group is dihedral of order 10, then the curve C sub k that parameterizes trinomials has exactly one rational point corresponding to this trinomial. So this is the only trinomial that defines this particular number field k. If you take the polynomial f of x equals x to the fifth plus 75x plus 105, then the number field k defined by it also contains the roots of this trinomial, and this one, 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 and this one. So there are in fact 8 different trinomials that define this number field that are all inequivalent. So when we have this map from rational numbers t to number fields, we have 8 different t values that map to the same field. So we certainly have, this is a pretty spectacular failure of injectivity. And I'll talk some at the end about why I think this injectivity fails, but I don't have a super clear understanding about what's special about this situation. I wanted to say a few things more about this. So Spearman and Williams found an infinite family of quintic fields defined by 2 inequivalent trinomials. So these are the fields of this form, the fifth root of r cubed times r plus 1 times r minus 1 to the fourth for some rational number r that's not 0, 1, or minus 1. And I found with my master's student, Jesse Podzolek, another family of polynomials where for every single parameter a, f1 and f2 define the same number field. So this is an infinite, so Spearman and Williams gave an example, and I gave another family of examples of situations where the injectivity fails. Okay. So the fourth example I want to talk about is for elliptic curves. So an elliptic curve E over Q is a curve of the form y squared equals x cubed plus ax plus b. I'm a number theorist, so I think of a and b here as being integers. The set of points on E has the structure of an abelian group. If I have 2 points on an elliptic curve, I can draw the line through those 2 points. If those 2 points are rational points, then the slope of the line through those points is rational. And that will guarantee that the third intersection point of that line with the curve is another rational point. And in this way, if you have points on a curve, you can generate more points. If I have a positive integer n, I'm going to let en denote the set of points on E defined over C with order dividing n. Because an elliptic curve is a genus 1 curve, that means that the group structure on E is isomorphic to C mod a lattice. And that forces it to be the case that there are precisely n squared points of order dividing n on E for every positive integer n. So there are lots of these points that have finite order. So despite the fact that there are lots of points on E that have finite order, you can't have more than 16 rational points of finite order on an elliptic curve because of this theorem of Mazur. So the points exist, but they're not very many of them are rational. They're in fact, the coordinates of these points in En are algebraic numbers. So if we adjoin to Q the x and y coordinates of all the points of order dividing n on E, that gives us a number field. It's actually a Galois extension of Q. And for every automorphism of this number field, the automorphism acts on the points En as an automorphism, thinking here of En as an abelian group. So that gives us the following. For each positive integer n, we have a homomorphism rho E comma n from gal q bar over q to the automorphism group of En, which is isomorphic to GL2 z mod nz, just by taking the automorphism sigma and restricting it to En. So this homomorphism is only defined up to conjugacy in GL2 z mod nz. We have to pick a basis for En as a free z mod nz module to fix the isomorphism between the automorphism group of En and GL2 z mod nz. And we can choose any basis we want to. There's no basis that's better or worse than any other. So another thing that's important to mention is that the only primes that ramify in this number field Q adjoin En are those that divide n and those for which the curve E has bad reduction. What that means is those are prime numbers P, where if you take the equation for E and reduce it mod P, you get a singular point. A singular point on a curve is a curve where there is no well-defined tangent line. Maybe it's a little weird to talk about tangent lines mod P, but algebraic geometers do it a lot. Okay. So the question now is, if you fix a positive integer n, is the map that goes from an elliptic curve over Q to this homomorphism from the Galois group to GL2 z mod nz, is this map injective? So if n is 2, 3, 4, or 5, Rubin and Silverberg wrote down infinite families of elliptic curves with the same rho E comma n. So for n small, this map is definitely not injective. For each elliptic curve E and for each positive integer n, there is a curve x E comma n whose rational points parameterize elliptic curves E prime, for which rho E comma n and rho E prime comma n are conjugate. So again, there's no way of naturally identifying the basis for En and the basis for E prime of n. So it doesn't necessarily make sense to call these functions equal, but we can talk about them being conjugate. So the genus of this curve x E comma n grows with n, and for n greater than or equal to 7, it has genus greater than or equal to 2. In fact, for n equals 7, it has genus 3. By Falting's theorem, the set of rational points on x E comma n is finite if n is greater than or equal to 7. And sort of when number theorists see that, they think, oh, okay, this is a curve that has genus greater than or equal to 2. Probably it doesn't have any rational points on it unless there's a reason it should. So Frey and Mazur asked if the map E maps to rho e comma p is injective if p is a prime number which is greater than or equal to 7. And that's a natural question to ask in light of Faltings' theorem. So it turns out, even in this situation, that the answer is no. So Krauss and Oesterle answered Mazur's question in 1992 with the example of these two elliptic curves, E1 and E2. These elliptic curves, E1 and E2, are not isomorphic, but their rho E7 functions are conjugate in GL2Z mod 7Z. Tom Fisher has done more work with this and has computed equations for the curve x e comma n for various small n, especially odd n, and given many further examples. And at this time, an example is known of elliptic curves E1 and E2 with rho E1 17 conjugate to rho E2 17, but none for p greater than or equal to 19. So it seems like Frey and Mazur's conjecture is perhaps true if you increase the bound on p that you require. Another interesting fact is there is exactly one example known of an E1 and an E2 for which rho E1 17 is conjugate to rho E2 17. We don't know if there's more than one. Okay. So the final example in talking about failure of injectivity, this is related to objects that help people understand these rho e comma n functions. If I choose a subgroup H of GL2Z mod NZ that contains minus the identity, then there is a modular curve Y sub H. Let me say what I mean by that. If I have a number field K, the K rational points of this curve are in bijection with pairs E and the class of iota, where EK is an elliptic curve, and iota is an isomorphism En to Z mod NZ squared, but there's an action of the subgroup H on those isomorphisms. And so the objects for that Y sub H classifies are pairs of elliptic curve and then this isomorphism. The curve Y sub H is not a projective curve. It can be made into a projective curve by adding finitely many cusps. And then you'll get a smooth projective curve. But these cusps correspond to like points that don't actually correspond to an elliptic curve. They correspond to elliptic curves that are singular in some way. So if you choose a subgroup H for which the determinant map is surjective, then XH is geometrically connected and it's defined over Q. The reason that this is important is that the rational points or the K points on these curves will help you determine the image of the rho E n maps that I talked about in example 4. So if you have an elliptic curve defined over a number field K, then it corresponds to a rational point on this curve if and only if the image of rho is contained in the subgroup H. Also, if you have one subgroup contained in another one, there's a natural morphism on the modular curves, which actually goes in the opposite direction from what I wrote at the bottom of this slide. So I apologize for that. These modular curves are special curves. They're not just any curve. Weight 2 modular forms can be thought of as holomorphic differentials on these modular curves x sub h. And Hecke operators, which are well known in the theory of modular forms, can factor through all of this machinery and give you endomorphisms of the Jacobian variety of x sub h. These modular curves also have bad reduction only at the primes that divide n. That's another important property. So the question now about whether this invariant associated to a subgroup is a complete invariant is whether the map from subgroups H of GL2Z mod NZ up to conjugacy to x sub h is injective or not. I could ask you to guess, but I have a feeling I know what people would guess. If you want to guess, go ahead and type your guess into the chat. Frank says no. Not surprisingly, Frank is correct. Okay. So I want to say something first. Suppose that I have two subgroups, H1 and H2, of GL2 L, Z mod L to the KZ. So here L is some prime number. And I'm going to let H1 tilde and H2 tilde be the full pre-images of these subgroups in GL2ZL. If H1 tilde and H2 tilde are conjugate in GL2QL, then the modular curves XH1 and XH2 are isomorphic. This is a weaker notion than requiring the subgroups H1 and H2 to be conjugate in GL2 Z mod L to the KZ. In this situation, the isomorphism between XH1 and XH2 are explained by isogenies. And then, of course, you can say, well, okay, so we have these other sort of natural ways that these modular curves could be isomorphic. Are all isomorphisms between modular curves explained in this way? And the answer is no. The most striking example of this is a paper that Bourchou-Baran wrote in 2014. So she computed equations for two very important modular curves, x non-split plus of 13 and x split plus of 13. So these are modular curves that correspond to the normalizers in GL2 Z mod 13Z of the group of diagonal matrices, that's the x split plus curve, and this group here, A2B minus BA, the normalizer in GL2 Z mod 13Z of that, that's this curve. One of the reasons that these curves are significant is that if you have an imaginary quadratic field with class number 1, that gives rise to an elliptic curve with complex multiplication. That gives rise to a rational point on one of these two curves. And which curve you get a rational point on is determined by whether 13 splits in that quadratic field or whether 13 is inert in that quadratic field. So if you could provably find all of the rational points on these two curves, you could solve the class number 1 problem. This was famously done by Baker, Heegner, and Stark in sometime between the late 50s and the early 60s. So the surprising thing is that these two curves, x split plus of 13 and x non-split plus of 13, are actually isomorphic. They're both isomorphic to this equation that I've given at the bottom of the slide. So this seems surprising. There's no natural reason why these should be isomorphic. The corresponding subgroups have different indices in GL2 Z mod 13Z. None of the elliptic curves whose rational points are parameterized by these have any isogenies. And so it's not possible to explain this isomorphism based on the stuff I talked about on the previous slide. And this is still something which I think is very mysterious. I should mention that Jennifer Balakrishnan and her collaborators have used the techniques from non-abelian Chaboty to provably find all of the rational points on this curve, which resolves the class number 1 problem, but also gives essentially complete information about the mod 13 Galois representations attached to elliptic curves. So there's some more examples. In 2012, David Zurich Brown and I determined all the rational points on modular curves necessary to determine the images of the row E2 to the N map. So the Galois representations mod powers of 2 for non-CM elliptic curves over Q. So we computed modular curves x sub h for hundreds of subgroups H. We found 52 subgroups H for which x sub h is an elliptic curve. Because our modular curves come from subgroups mod a power of 2, these elliptic curves will have bad reduction only at the prime 2. But there are only 24 elliptic curves over Q that have bad reduction only at 2. And so this map from subgroups to modular curves cannot possibly be injective. Here's one more example. This is a genus 3 curve, and this arises as x sub h for 4 pairwise non-conjugate subgroups H of GL2 Z mod 32Z. It took a lot of effort for us to provably find all the rational points on this elliptic curve, this curve, and in fact there are 6. In 2 cases, the 6 rational points on this curve correspond to elliptic curves with complex multiplication. In the other 2 cases, the curve has 2 rational cusps, 2 rational CM points, and 2 rational non-CM points. The isomorphisms between these curves that I talked about in connection with isogenies earlier, those isomorphisms will have to send CM points to CM points and cusps to cusps. And so while two of these, we have these 4 curves, and we can break them up into 2 pairs. And those 2 pairs are isomorphic because of reasons related to isogenies. But looking at curves between the pairs, there is no way to explain it that way. So this is another sort of unexplained situation where we get curves that are isomorphic without having a good reason why. Okay. So in the remaining part of my talk, I'd like to just give you some thoughts I have about reasons that injectivity fails. I have 2 reasons that I can explain that I hope are reasonable and that might possibly shed light on other problems. So the first reason is geometry. So I feel like this reason does a good job of explaining the situation with the trinomials that I talked about and with the mod n Gauss representations to elliptic curves, the 4th example. So in the first case, for each number field k, we have this curve c sub k, whose rational points give trinomials that define k. And in the second case, there's this curve x e comma n, whose rational points parameterize elliptic curves e prime, so that the mod n Gauss representation for e prime is the same as that for e. Somehow this is maybe the wrong thing to look at. It's more natural to ask for a geometric object that parameterizes pairs t and t prime, so that these trinomials define the same number field. This would be an object that has, instead of 1 parameter, 2 parameters. Such an object exists, and it's a surface x. And the failure of injectivity can be explained if this surface has lots of points on it. So this surface x is a degree 2 K3 surface. You can find a model for this surface of the form y squared equals f of x comma t, where f is a homogeneous polynomial in 2 variables of degree 6. This is maybe surprising. K3 surfaces are not like completely general surfaces. They're surfaces that have a lot of extra structure to them. It's conjectured that if x over q is a K3 surface, then the rational points on x are potentially dense. That means that you can find a number field k so that the points on x over k are not restricted to a finite set of curves. So you can do the same thing with modular curves. So when you're looking at the function rho e comma n, the same approach gives insight. For each integer n, there's a surface zn. Technically, it's not necessarily connected. It might have multiple irreducible components, with the property that the points on zn of k are in bijection with pairs of curves e and e prime that have the same mod n Gauss representation. So Halberstadt and Krauss showed that for n equals 7, one of the irreducible components of Z7 is a rational surface, a surface that's birational to P2. And that means that you can give a complete parameterization for all of its points. And in particular, it has to have lots of points. So even though the fibers of this surface, if you pick one specific elliptic curve, are curves of higher genus, which forces them to only have finite many points. So all of these curves live on a surface which is somehow much simpler. Connie and Rizzo showed that for n equals 11, one of the irreducible components of Z sub n is an elliptic surface, which is sort of like take an elliptic curve and then instead of having a and b be integers, have them be rational functions. They also showed that this elliptic surface has infinitely many sections. So the group of like rational functions on the curve, points whose coordinates are rational functions on the curve, is infinite. In a recent preprint, this isn't published yet, Tom Fisher has written down equations for the 2 irreducible components of the surface Z13. These are surfaces of general type, completely generic surfaces. It's believed that surfaces of general type should not have very many points on them. However, Fisher found one rational curve on each component, and these rational curve gives infinite families of pairs E and E prime where the mod 13 Gauss representations attached to them are the same. So I want to talk about the second reason that I think that the injectivity can fail. So I want to go back to an article that Richard Guy wrote in the Monthly in 1988, where he introduced his notion of the strong law of small numbers. So he says that there aren't enough small numbers to meet the many demands made of them. This is one of his statements of the strong law of small numbers. So you can have two small numbers that are equal, but not necessarily for a good reason. He talks about this mainly in the context of sequences of numbers that might look the same but actually aren't. But I feel like this principle, there aren't enough small numbers to meet the many demands made on them, is a natural one, and we can take it to a new context. So as I said, two small natural numbers could be equal by chance. One example that comes to my mind is that 1 squared plus 2 squared plus 3 squared all the way up through 24 squared, that's equal to 4,900, which happens to equal 70 squared. Those numbers are both fairly small, and so they could happen to be equal by chance. It turns out that 70 squared is the largest number, which is a perfect square, and also a sum of consecutive squares starting at 1. So I want to modify Richard Guy's principle. So I'm going to say there aren't enough small number fields, k over q, to meet the demands that are made of them. So in particular, if you put restrictions on the primes that can ramify in k over q, and you put restrictions on the Galois group of the Galois closure of k over q, there may be few or no number fields that are left that meet your restrictions. So here's an example of that. Suppose that I have an elliptic curve e over q that has bad reduction only at the prime 2. I mentioned earlier that there were 52 modular curves that David Zork-Brown and I compute that have this property. I claim that any elliptic curve over q that has bad reduction only at the prime 2 must have a rational point of order 2 on it. This is a rare property. 0% of elliptic curves defined over q have a rational point of order 2 on them. Here's why. If E had no rational point of order 2, then since E over C has 3 points of order 2 on it, those 3 points would form a single Galois orbit. The stabilizer of that Galois orbit would have to be a degree 3 extension of Q, which is ramified only at the prime 2. But there aren't any number fields like that. There are no degree 3 extensions of Q ramified only at 2. In fact, the smallest odd number which occurs as the degree of a number field ramified only at 2 is 17. This is one reason I think that the project that I worked on with David Zork-Brown ended up being successful in the end. There are a lot of places that we got very lucky. But we didn't get lucky just because we got lucky. We got lucky for a reason. Maybe I'll say that. So I believe that this sort of strong law of small number field explains the lack of injectivity in example 1 about the quadratic forms and example 5 about the modular curves. And I'll try to explain a little bit more about why that's the case. So the situation with the number fields that have the same Dedekind zeta function has a slightly different explanation. And the paper of Perlis that I mentioned, I think, has a good explanation for the lack of injectivity there. Although there might be a little bit of overlap between what's really going on in those examples and also with examples 1 and 5. So in example 1, the theta series attached to the quadratic forms, those have Galois representations attached to them. They're not irreducible representations like those attached to elliptic curves or attached to new forms, but those Galois representations will determine the number R sub q of n mod m for any positive integer m that you like. The ramification of the fixed fields of those representations is determined by the discriminant. The two quadratic forms in question in Schemann's example have discriminant 1,729. There are 175 quadratic forms that have discriminant 1,729. And there are a lot of restrictions that are placed on the Galois representations that could be associated to those things. And so perhaps it's not so surprising that two such quadratic forms actually have equal theta series. Going to example 5 about the modular curves. For an arbitrary curve C over Q, there are Galois representations acting on torsion points, points of finite order, not on the curve, but on the Jacobian of the curve. The mod P Galois representation has a fixed field ramifying only at the prime P and at primes of bad reduction for the curve C. If the curve C has extra endomorphisms, the image of these Galois representations will be forced to be smaller. In the case of modular curves of level 13, the mod 13 Galois representations can be ramified only at 13, and that forces them to have fairly small image. I looked in databases of number fields for number fields ramified only at 13. I think that there are 8 examples of number fields ramified only at 13 in the L functions and modular forms database. And of the ones whose degree is not a multiple of 13, the only ones that are known or that are listed there are subfields of Q adjoins zeta 13. Here's another reason why I think that this is part of what's going on. There is in fact a third genus 3 modular curve of level 13 arising from a different subgroup, different than x split plus of 13 or x non-split plus of 13. This genus 3 modular curve with bad reduction only at 13 is not isomorphic to either of these x split plus or x non-split plus modular curves. However, it has the same Galois representations at all primes. And hence, it has the same number of points on it mod P for all primes P as the x split plus and x non-split plus curves. I still don't completely understand this phenomena. It seems surprising, and I don't know that people have a super convincing explanation for it, but this is sort of what I think is going on. As a summary, we've discussed 5 different situations. We've talked about quadratic forms, we talked about number fields, we talked about trinomials, we talked about the row E comma n, and we talked about modular curves, where the natural invariants fail to distinguish non-isomorphic objects. So I listed those just a moment ago. There are 2 natural reasons why I think these invariants fail to classify. One of them is considering the geometry of classifying pairs of objects with equal invariants, and the other is the strong law of small number fields. So thank you very much for coming and listening.
Thank you very much. If somebody wants to talk or ask a question, you'll need to unmute yourself. Let's all give him some kind of round of applause with our appropriate emoji. Are there any questions?
Yeah. So I'll ask you a question. So you raised this very interesting prospect of when you don't have injectivity, often there is some nice geometric space parameterizing pairs with the same invariant. So here's an example where I'd be widely excited to find such a space. Consider binary cubic forms up to equivalence, so integral binary cubic forms. Then the question is, does this discriminant classify these? And the answer is no. And so one wants bounds on the multiplicity of how many there are of a fixed discriminant. And this would have, as you know, about implications for 3 torsion and quadratic fields. Parameterized pairs of these, then maybe you could do something cool with it. Do you speculate that such an object exists?
This is a good question. So I feel like a slightly related question is, let's say you were just trying to parameterize in some way like unramified extensions of a number field.
Yeah.
And you wanted some sort of geometric object. You could be asking a question like, is there like a scheme or a stack with the property that the k points on that scheme or stack is a finite set in bijection with the class group? I think that's a great question. I think that Jared Weinstein has answered it, and the answer is no.
How do you answer that in the negative? Like prove that there's no moduli space?
I don't know. I mean, I confess I haven't even read the paper that I'm vaguely alluding to.
Okay.
Alex had a question.
Yeah, this is a little bit. So you mentioned there was a number field in the first, I think the second example where you were looking at the, yeah, I guess the theta series. No, not the theta series. The zeta. Sorry, the zeta series that associated. And you said that it one of the curves that of degree 7 that showed up had PSL27 or well, you said GL3.
F2, yeah.
Yeah.
GL3 of F2 and PSL2 of F7 are isomorphic.
Right, exactly. But you only mentioned one of them. Are they also different Galois groups, or do they just have the same Galois? Because that would
they have the same Galois group. In fact, so any two arithmetically equivalent number fields have to have the same Galois closure.
Okay, that's
not only is it the same group, it's actually the same Galois extension in the end.
I see. Okay, that's basically what I was asking. Yeah, that's it.
Could you comment on, I guess, how badly injectivity fails? And you mentioned in one of the results you when you were talking about elliptic curves, but for example, with the theta series, can you have an arbitrary number of where each pair is non-isomorphic and have and the injectivity fail for all of them at the same time?
Yes. So I think that if you put no restriction on the dimension of the quadratic forms, I think it's actually fairly easy to do this. In fact, if you just look at, say, quadratic forms where the dimension is a multiple of 8 and the discriminant is 1, and you let the dimension grow, I believe that the number of quadratic forms with discriminant 1 in that dimension grows much faster than the number of theta series that you can have. I'm not absolutely certain about that, but it's an interesting question to look at. And so I think you'll have sort of arbitrarily bad failure of injectivity.
Do you think that's true of all the topics you talked on, or?
No. So people conjecture that if you fix a genus of a curve, there's an absolute bound on the number of rational points on a curve of genus G. And that would mean that in the example of trinomials, or in the example of elliptic curves with the same row e comma n, if you fix an n, or if you affix a degree of the trinomial, there's an absolute bound on the number of elliptic curves or trinomials that have the same invariant.
Other questions? Now maybe we can give Jeremy another round of applause.
Thank you.
Thank you. Thank you very much for talking, and we appreciate it. Let's see, how do I stop the recording here?